Langchain Mistralai Chat models. Description: Langchain Mistral AI chat models are a type of large language model (LLM) specifically designed for conversational interactions. They leverage the powerful capabilities of Mistral AI's language models, combined with Langchain's framework, to enable seamless integration with various data sources and tools. This integration empowers these models to engage in comprehensive and informative conversations, drawing upon external knowledge and executing tasks as needed. Inputs. User input: this is the text input provided by the user, initiating the conversation. It could be a question, a statement, or a command. Context: Langchain Mistral AI chat models can take advantage of past interactions to maintain context and provide more coherent responses. This context might include previous user inputs, relevant documents, or other data sources. Outputs. Text response: the primary output is the generated text response, providing information, answering questions, or executing tasks based on the user's input and the available context. Actions: depending on the task, the model might also output actions. This could involve fetching data from an API, accessing a database, or executing specific commands. Steps. Input processing: the user's input is tokenized and processed to extract meaning and identify the user's intent. Context retrieval: depending on the model's configuration and the context available, relevant information is fetched from external sources, such as documents, databases, or APIs. Response generation: the Mistral AI model generates a text response based on the processed input, the retrieved context, and the learned knowledge from its training data. Action execution: if the model identifies a task to be performed, it executes the appropriate actions, such as retrieving data from an API or interacting with a database. Metrics. Accuracy: evaluating the accuracy of the responses generated by the model, assessing how well it answers questions and fulfills requests. This might involve comparison against known correct answers or human evaluations. Coherence: analyzing the flow and consistency of the conversation. A coherent response avoids abrupt transitions and maintains a logical thread, making the conversation feel natural. Relevance: assessing whether the model provides information relevant to the user's input and the context of the conversation. Visualization plots. Conversation flow diagram: visualizing the progression of the conversation, showcasing how different inputs and context elements contribute to the generated responses. Attention maps: illustrating how the model focuses on specific words or phrases in the input and context to generate its response. This can help understand the model's reasoning process. Fine-tune parameters. Learning rate: this parameter controls how quickly the model adapts to new data during fine-tuning. Epochs: the number of times the model iterates over the training data during fine-tuning. Batch size: the number of training examples processed in each step of fine-tuning. Uncertainty methods. Temperature sampling: a technique that introduces randomness in the model's output, making it explore different possible responses. This can be useful to quantify uncertainty in the model's predictions. Ensemble methods: using multiple models to generate responses and then combining them to get a more reliable and less uncertain prediction. Challenges and fixes. Challenge 1: hallucination. This occurs when the model generates false information or makes up facts. Sample use case that resulted in challenge 1: the user asks a question about a specific historical event, and the model provides incorrect details. Fixes to challenge 1. Fact verification: incorporate mechanisms to verify facts generated by the model against reputable sources of information. Training data quality: ensure that the training data used to train the model is accurate and free from biases. Challenge 2: bias: the model might exhibit biases based on the data it was trained on. Sample use case that resulted in challenge 2: the model generates responses that perpetuate stereotypes or discriminatory attitudes. Fixes to challenge 2: data augmentation: augment the training data with diverse perspectives and counter examples to mitigate bias. Bias detection tools: utilize tools and techniques to identify and address potential biases in the model's output. Challenge 3: limited context: the model might struggle to maintain context across a long conversation, leading to inconsistent responses. Sample use case that resulted in challenge 3: the user has a conversation with the model about a specific topic, but the model forgets previous interactions and provides irrelevant responses. Fixes to challenge 3: memory mechanisms: implement mechanisms to store and retrieve relevant information from past conversations. Enhancing context awareness. Contextual prompts: design prompts that explicitly provide the model with the necessary context to generate coherent responses. Langchain Mistralai Chat models: Chat Mistral AI. Description: Chat Mistral AI is a Langchain wrapper for Mistral is open source large language models. It provides a simple interface for interacting with Mistral AI models through Langchain, enabling developers to leverage the power of Mistral AI models in their applications. Inputs: prompt: the user's input query, which is passed to the Mistral AI model for processing. Model name: the name of the Mistral AI model to use for the chat interaction. This allows users to choose from different models based on their specific needs and capabilities. Temperature: a parameter that controls the creativity and randomness of the model's responses. Higher temperature values lead to more creative and diverse responses, while lower values produce more predictable and consistent outputs. Top: a sampling parameter that influences the selection of tokens during the generation process. It limits the probability distribution of the next token to the top p most likely tokens. This helps to improve the quality and coherence of the generated text. Top: a sampling parameter that selects the top k most likely tokens for generating the next token. It encourages the model to generate more diverse and interesting responses by considering a wider range of possibilities. Max tokens: the maximum number of tokens the model can generate in a single response. This parameter helps to control the length and verbosity of the generated text. Outputs: response: the generated text response from the Mistral AI model, based on the user's input query. Steps: the user provides their input query through the prompt parameter. The specified Mistral AI model is loaded using the model name parameter. The model processes the input query and generates a text response based on its training data and the provided parameters. The generated response is returned to the user. Metrics: perplexity: a measure of how well the generated text matches the statistical properties of a language model's training data. Lower perplexity values indicate better fluency and coherence. Blue score: a metric that evaluates the quality of machine translation by comparing the generated translation to human-generated reference translations. Higher blue scores indicate better translation quality. Rouge score: a metric that measures the similarity between generated text and reference text, often used to evaluate summarization or question-answering tasks. Higher rouge scores indicate better similarity to the reference text. Visualization plots: attention visualization: this plot displays the attention weights assigned by the model to different parts of the input query, providing insights into the model's reasoning and decision-making process. Token probability distribution. This plot shows the probability distribution of the next token at each step of the generation process, revealing the model's preferences and the uncertainty associated with its predictions. Fine-tune parameters. Learning rate. The step size used during model training, controlling how quickly the model's weights are adjusted to minimize the loss function. Batch size. The number of training examples processed in each iteration of the training process. Epochs. The number of times the entire training dataset is presented to the model during training. Uncertainty methods. Temperature scaling. Adjusting the temperature parameter during generation can reveal the model's uncertainty by producing more diverse and less confident responses at higher temperatures. Token probability. Examining the probability distribution of the generated tokens can provide insights into the model's confidence level, with lower probabilities indicating greater uncertainty. Challenges and fixes. Challenge 1. Generating repetitive or incoherent text. Sample use case. When prompted with a simple question like "What is the capital of France?" the model might produce responses that include irrelevant information or repeat the same phrase multiple times. Fixes. Adjust the temperature parameter to encourage more creative and diverse responses. Increase the maximum number of tokens allowed for generation to provide the model with more context and flexibility. Challenge 2. Misinterpreting ambiguous prompts. Sample use case. When asked "Tell me about the cat in the hat," the model might provide information about a different type of cat or misinterpret the intent of a prompt. Fixes. Fine-tune the model on a dataset specifically tailored to the desired domain or task. Use prompt engineering techniques to provide clearer and more specific instructions to the model. Challenge 3. Lack of factual accuracy. Sample use case. The model might provide incorrect information about historical events or scientific facts. Fixes. Train the model on a dataset with high-quality factual information. Use techniques like knowledge distillation to transfer knowledge from more accurate models to the target model. Challenge 4. Generating offensive or harmful content. Sample use case. The model might produce responses that contain hate speech, discriminatory language, or violence. Fixes. Implement safety mechanisms to detect and filter out harmful content. Train the model on a dataset that includes examples of both positive and negative content to teach it to distinguish between appropriate and inappropriate language. Langchain Mistralai Chat models a completion with retry. Description. This chain combines a Mistral AI chat model with a retry mechanism, allowing for more robust interactions when encountering errors. Inputs. Prompt the user's input for the chat model. Max retries. The maximum number of attempts to retry the model call if an error occurs. Outputs. Response. The generated response from the Mistral AI chat model. Error. Any error encountered during the process. Steps. Initialize a counter for the number of retries. While the number of retries is less than the maximum allowed retries, try to call the Mistral AI chat model with the provided prompt. If the call succeeds, return the response. If the call fails, increment the retry counter and log the error. If the maximum number of retries is reached, return the last error encountered. Metrics. Retry rate. The percentage of model calls that resulted in retries. Average response time. The average time taken for the model to generate a response, excluding retries. Error rate. The percentage of model calls that resulted in an error. Visualization plots. Retry count distribution. A histogram showing the number of retries per model call. Response time distribution. A histogram showing the distribution of response times. Error rate over time, a line graph showing the error rate over time. Fine-tune parameters. Max retries, the maximum number of attempts to retry the model call if an error occurs. Retry delay, the delay between each retry attempt. In seconds. Retry backoff factor, a multiplier applied to the delay after each retry. Uncertainty methods. None. Challenges and fixes. Challenge: one model may fail due to network issues or temporary server downtime. Sample use case: a user attempts to interact with the chat model, but the server is experiencing temporary downtime. Fixes: retry the model call after a short delay. Implement exponential backoff to gradually increase the delay between retries. Challenge: 2 model may fail to generate a response due to internal errors. Sample use case: a user attempts to interact with the chat model, but the model encounters an internal error and fails to generate a response. Fixes: retry the model call after a short delay. If the error persists, log the error and return an appropriate message to the user. Challenge: 3 model may generate an incorrect or irrelevant response. Sample use case: a user asks the chat model a question about a specific topic, but the model generates a response that is unrelated to the topic. Fixes: this is not a retriable error. The model's response should be evaluated and appropriate feedback should be provided to the user. Langchain Mistralai embeddings. Description: Langchain Mistral AI embeddings are a powerful tool for embedding text and code using Mistral AI's large language models (LLMs). These embeddings are vector representations of the input text, capturing semantic meaning and allowing for tasks like similarity search, clustering, and classification. Inputs: text. The input text to be embedded. This can be a single sentence, a paragraph, or a longer document. Model: the specific Mistral AI model to be used for embedding. Different models have varying capabilities and may be better suited for specific tasks. Outputs: embeddings. A list of numerical vectors, one for each token in the input text. The length of the list is determined by the tokenization method. Metadata: additional information about the embedding process, such as the model version used, tokenization details, and embedding dimensions. Steps: tokenization. The input text is split into individual tokens using a predefined tokenizer specific to the selected Mistral AI model. Encoding: the tokens are passed through the Mistral AI model, generating corresponding numerical vectors. Each token is mapped to a unique vector representation. Metrics: cosine similarity, a common metric used to measure the similarity between two embeddings. Values range from 0 to 1, with 1 indicating perfect similarity. Euclidean distance, another metric for comparing embeddings, measuring the distance between them in vector space. Visualization plots: scatter plot visualize relationships between embeddings in a 2D or 3D space. Can be helpful for clustering and understanding semantic relationships between texts. TSNE plot, a dimensionality reduction technique used to visualize high-dimensional embeddings in a lower dimensional space while preserving relative distances. Fine-tune parameters: embedding dimension, the number of dimensions in the output embedding vectors. Higher dimensions can capture more nuanced information but require more computational resources. Model size: the size of the Mistral AI model used for embedding. Larger models generally provide better performance but may have higher latency. Uncertainty methods: confidence scores. Some Mistral AI models can provide confidence scores for each token's embedding, indicating the model's certainty about the generated representation. Ensemble methods: combining multiple embeddings from different models can improve robustness and reduce uncertainty. Challenges and fixes. Challenge 1: Insufficient memory for large documents. Sample use case that resulted in challenge 1: Embedding large documents with many tokens might exceed available memory. Fixes to challenge 1. Chunking: divide the document into smaller chunks and embed each chunk separately. Then combine the embeddings using techniques like mean pooling or concatenation. Streaming: use a streaming approach to process the document piece by piece, avoiding loading the entire document into memory at once. Challenge 2: Data leakage. Sample use case that resulted in challenge 2: Embedding sensitive information might lead to unintended leaks if the embedding is used for downstream tasks. Fixes to challenge 2. Differential privacy. Apply differential privacy techniques to the embedding process to add noise and protect sensitive information. Data obfuscation. Pre-process the input text by replacing sensitive words or phrases with generic alternatives. Challenge 3: Model bias. Sample use case that resulted in challenge 3: Using embeddings from a model trained on biased data might lead to biased downstream applications. Fixes to challenge 3. Bias mitigation techniques. Use techniques like adversarial training or debiasing methods to mitigate biases in the embedding model. Data augmentation. Augment training data with diverse examples to reduce bias in the models. Representation. Langchain Mistralai Embeddings Dummy Tokenizer. Description: the dummy tokenizer is a placeholder tokenizer used within the Mistral AI embedding functionality. It essentially functions as an identity mapping, meaning it directly outputs the input without any processing or tokenization. This approach is particularly useful during initial development or testing phases, where the focus is on the embedding functionality itself without the complexities of actual tokenization. Inputs. Text input: the raw text that needs to be embedded. Outputs. Tokenized text returns the same input text as it is, without any tokenization. This mimics the behavior of a tokenizer but simplifies the process for early experimentation. Steps. Input handling: the dummy tokenizer receives the raw text as input. Identity mapping: it directly passes the input text through without performing any tokenization or modification. Metrics. The dummy tokenizer doesn't have any specific metrics associated with it as it doesn't perform actual tokenization. Visualization plots. The dummy tokenizer doesn't generate any visualizations. Fine-tune parameters. The dummy tokenizer is not designed to be fine-tuned. Uncertainty methods. The dummy tokenizer does not incorporate any uncertainty estimation methods. Challenges and fixes. Challenge 1: Lack of tokenization. The dummy tokenizer might not be suitable for tasks that heavily rely on tokenization, such as language modeling or sentiment analysis. Sample use case that resulted in challenge 1: Implementing a BERT model that requires a proper tokenizer for word segmentation and embedding generation. Fixes to challenge 1: Replace the dummy tokenizer with a real tokenizer from a library like transformers or tokenizers. This will provide the necessary tokenization for the embedding process. Challenge 2: Limited feature engineering. The dummy tokenizer doesn't allow for any advanced feature engineering techniques that might be crucial for certain embedding models. Sample use case that resulted in challenge 2: Creating embeddings for a model that needs to consider subword information or special characters for better performance. Fixes to challenge 2: Utilize a more sophisticated tokenizer that can handle subword segmentation, character-level tokenization, or other feature engineering methods according to the specific embedding model requirements. Langchain Mistralai Embeddings Mistral AI Embeddings. Description: Mistral AI Embeddings is a Langchain embedding class that utilizes the Mistral AI embedding model to generate vector representations of text data. Inputs: text, the input text for which embeddings are generated. It can be a single string or a list of strings. Outputs: embeddings, a list of numerical vectors, one for each input text. Each vector represents the semantic meaning of the corresponding text. Steps: the input text is sent to the Mistral AI embedding API. The API returns a list of numerical vectors representing the semantic meaning of the input text. Metrics: accuracy. The accuracy of the embeddings can be evaluated by comparing the embeddings of similar texts. This is done by computing the cosine similarity between the embeddings. Higher cosine similarity indicates closer semantic meaning. Performance: the time taken to generate embeddings can be measured to assess the performance of the embedding model. Visualization plots. Embedding visualization: embeddings can be visualized in a multi-dimensional space using dimensionality reduction techniques like PCA or TSNE. This helps in understanding the semantic relationships between different texts. Fine-tune parameters. Model size. Different versions of the Mistral AI model have different sizes, influencing the quality and speed of embeddings. Embeddings dimension. The dimension of the output vectors can be adjusted to control the complexity of the embedding representation. Uncertainty methods. Confidence scores. Some embedding models provide confidence scores for the generated embeddings, indicating the certainty of the model in its prediction. Ensemble methods. Using multiple embedding models and combining their outputs can help in reducing uncertainty. Challenges and fixes. Challenge 1: the Mistral AI embedding model may not be available in all regions, leading to connection errors. Sample use case that resulted in challenge 1: a user in a restricted region tried to use the Mistral AI embeddings class and received an error. Fixes to challenge 1: use a VPN to access the model from a different region. Challenge 2: the embedding model may not be optimized for all languages, resulting in reduced accuracy for non-English texts. Sample use case that resulted in challenge 2: a user tried to embed a Chinese text and the output embeddings were not accurate. Fixes to challenge 2: consider using a different embedding model specifically designed for the target language.